Good morning or afternoon or evening. This is Mrs. Sharp. We are going to continue our notes here in 5.4. Part 3, going to be discussing some polarity. So the question is here, and where we're going to start off notes is, what if two atoms in a covalent bond don't share equally? And so we have some new terms I want to introduce you to, and feel free to pause as you write these down, but some important definitions. First is polar. A polar covalent bond, polar, is when you have an unequal sharing of electrons. The electrons spend more time with one atom than another. And I'm just going to add a little note here. This is because of a difference in electronegativity between 0.4 and 1.7 of two non-metals. Okay, so when two non-metals have such a large difference in electronegativity that the difference between them is between 0.4 and 1.7, then that's going to result in them sharing unequally. If they share pretty much equally, an equal sharing of electrons, we're going to call that a nonpolar covalent bond. And so equal, I'm going to put in quotations, because for electronegativity, that's a difference of 0 to 0.4. So as you can see, it can have a small difference, so it can be slightly unequal, but it's so small, it's such a small difference that the atoms don't really notice. So if it's between 0 and 0.4, we're going to pretty much think that that's sharing equally. If it's bigger than that, 0.4 to 1.7, that's going to be considered an unequal sharing. And the electron is going to spend the most time around the atom with the higher electronegativity. Here's an analogy for you to consider. You don't have to write this down in your notes, but here's an example. Two students share a textbook. Determine which situation stands for polar and which situation stands for nonpolar. Situation number 1. One student gets to bring the textbook home 1 week, and the other student gets to bring the textbook home the following week. Analogy, or situation 2, one student gets to bring the textbook home 3 nights out of 5. So that would stand to reason that the other student gets it only 2 nights out of 5. Now, thinking about that, situation number 2 would be polar because those students are sharing unequally. One student gets the textbook a lot more often than the other, and we can assume that if the class is based on the book, then he or she would do better in the class. Situation 1, they're sharing exactly equally. So that would be a nonpolar situation. Here's an example, and I would like for you to redraw this Lewis structure here. But this is called a nonpolar covalent bond, and I want you to look at the difference in electronegativity here. So chlorine has an electronegativity of 3.16. So does chlorine. Haha. So those electrons are being shared 100% equally, because both chlorines are pulling on them the exact same amount, so they're going to stay right here halfway in between. Neither chlorine feels like it has the electrons more than the other. So it's the textbook example where each student is getting those electrons an equal amount of time. So we're calling that a nonpolar bond because they're equally shared, and covalent because they're still shared. So this nonpolar just is kind of a describer of the covalent. They're shared, and they're shared equally. Let's look at another example while I try to fix this here. Hydrochloric acid, HCl, is a polar covalent bond, so I want you to look at what's going on here. Here's the Lewis structure for HCl. Drawn it for you. H has an electronegativity of 2.2. Cl has an electronegativity of 3.6. They are both nonmetals, and the difference is 0.96, which puts us in the polar range, 0.4 to 1.7. So what that means is that chlorine, and the way that I've drawn it here, you can see the electrons are spending more time with the chlorine atom. So the chlorine atom is feeling like he has those electrons more than the hydrogen atom. So what we do is we draw an arrow if it's bigger than 0.4. You don't draw an arrow if the difference isn't bigger than 0.4, because remember that means they're sharing equally. If they're sharing unequally, we draw the arrow so that it's pointing to who is hogging the electrons. So in this case, chlorine is hogging the electrons. So we're going to draw the arrow towards chlorine, and we're going to make this little symbol that looks like you're drawing a figure 8, but then you just stop in the middle. And that means kind of, or partial. Whoops. So that little symbol right there means kind of or partial charge. Whoops. And we're going to say it's kind of or partially negative because that's where the electrons are going. So the electrons are spending more time. Okay, they're not stolen completely, so chlorine isn't all the way negative. It's not stealing the electrons, but since it's hogging them, it gets that partial negative. Now hydrogen feels like it's sort of losing out on the electrons, so we do the same little symbol and we give it a positive. So it's partially positive. Not all the way, but sort of. Okay, so looking at some more pictures here, we've got our little symbols here, and you can see that those are much better drawn than mine. So we can see that this H right here is a student with more homework, and the book spends less time at that house. And then the book is spending more time at chlorine's house, so that student would feel better off. Or you can think of it as a tug of war where hydrogen is obviously losing, if you see this drawing here. Now these guys are strong enough where they're not going to let go completely and give up, but they're doing a lot of work, and that red flag is definitely moving over to the chlorine side. That is called a polar covalent bond. So on your periodic table, I need for you to, down in the bottom, to mark up your little scale. It says percent ionic character of a chemical bond. And so between the 0.4 and the 0.5, I need for you to make a solid vertical line there. And I also need you to make a solid vertical line between 1.6 and 1.7. And I need you to label anything below 1.7 as covalent and anything above 1.7 as ionic. And then to be even more specific, between 0 and 0.4, we're going to call that nonpolar and covalent. And between 0.5, or anything above 0.4 and 1.6, we're going to call that polar covalent. What happens is that when you get here, the electronegativity difference is so big that eventually that electron is just stolen completely. Not hogged, but stolen. So we have electron shared, electron hogged, and electron stolen. That's the difference between those three types of bonds. So they're all shared in covalent, just equally and unequally. Here, they're not shared at all. They're stolen. So if you mark that on your periodic table, I think that will really help. Okay, so I want you to practice. It says, what type of bond is this? Draw arrows like. And go ahead and pause and see how you did. So you're going to draw your arrow, and then you're going to label it sort of positive or sort of negative. Ready, set, go. Okay, so time to check our answers. First one, N to Cl. N has a lower electronegativity than chlorine, and that's a difference of 0.5 because N is 3.0 and chlorine is 3.5. Oh wait, hold on, I don't know if that's right. I might be remembering wrong. Whoops. You know what? I'm so sorry on this one. I messed up. This one right here would not have an arrow because N is 3.0 and Cl is 3.0. So this one would have a difference of electronegativity in 0, which puts it in the 0 to 0.4 range, which means it is nonpolar. So we would not draw an arrow. Situation number 2, we have a metal lithium, which is a 1.0 electronegativity, and oxygen, which is a 3.5. That's a difference of 2.5, which makes this ionic. So we wouldn't have an arrow because oxygen would just steal those electrons completely and have a full-out negative charge. I didn't draw it very well, but instead of that symbol for partial, we're just going to write negative and circle it. Just like here for lithium, we're not going to write a partial positive. We're going to write an all-the-way positive because its electrons are going to be stolen. Okay, S and O. S has an electronegativity of 2.5. and O is 3.5, so that difference is 1.0, which makes it polar covalent. So this one does get an arrow, and it should be going towards the O because it has the bigger electronegativity, which makes it partially negative. The S then is partially positive. And then finally, we have 2.1 for hydrogen, and we have 4.0 for fluorine. And so that is going to be a difference of, oh, I screwed up again. That's going to be a difference of 1.9. And so that's going to be considered ionic. So fluorine is going to be all the way negative. Hydrogen is going to be all the way positive. And there'll be no arrows to draw in this situation. So we're going to talk about this some more tomorrow, but I would like for you to be prepared for a short quiz on what we have done here. So you can use your notes. It's open note. But any questions you have over that too, we'll go over because we're going to move on from here tomorrow in notes. But you have to have seen this first, otherwise the notes we take tomorrow in class ain't going to make no sense. So there you go. Have a lovely evening, afternoon, morning, whatever it is, and I will talk to you soon. Bye-bye.